Alright, so for Project 11, I've elected to do a video tutorial on creating Lewis structures. So I've gone ahead and listed the key procedures as Dr. Knuckley highlighted in his notes. Number 1, sum the valence electrons from all of the atoms. Number 2, write the symbols for the atoms, show which atoms are attached to which, and connect them with a single bond. Number 3, complete the octets around all the atoms bonded to the central atom. Number 4, place any leftover electrons on the central atom. And number 5, if there are not enough electrons to give the central atom an octet, try multiple bonds. So as we go throughout these 4 key examples that I've elected to do, these are just going to play a part, and we're going to go through the same steps each and every time. One key thing to remember, and one principal idea of Lewis structures when you're doing them, is the octet rule, which states that atoms tend to gain, lose, or share electrons until they are surrounded by 8 valence electrons. So remember, they're trying to get to that noble gas balanced state. So here we go. We've chosen four examples to do, and I've went ahead and listed out some of this information just for the sake of time, because these can get pretty lengthy and because I'm doing 4 examples instead of 1. So the first example is going to be just a common Lewis structure. So from our procedures, we know that the first thing we have to do, and by the way, we're doing nitrogen trichloride, or NCl3. So the first thing we have to do is we have to sum the valence electrons from all of the atoms. So here we know that one nitrogen atom has 5 electrons, and one chlorine atom has 7 rather, because it has -1 charge and this has a +3 charge respectively. So if we have 3 times 7 is 21, 1 times 5 is 5, we sum these, and we now know that we have 26 electrons that we have to account for in this Lewis structure. So our next step is going to be to write in the least electronegative atom in the center. So in this case, that gives us nitrogen, and then it's going to be surrounded by 3 chlorines. So we went ahead and made those bonds, so that accounts for 6. So we have 2, 4, 6 gone. So now we're down to 20. And we know because of the octet rule that we have to satisfy that there's going to be 8 on each of these. So we go ahead and fill that in. That gives us 2, 4, 6, 8, 10, 12, 14, 16, 18. And then remember we have the 3 bonds, so 20, 22, 24. And we know we had 26. So now, by filling another 2 for nitrogen, that satisfies the octet rule for each and every individual atom. And we come up with the right number of electrons. So this one's easy, everything balances out, it's nice and simple. But within the octet rule, there's a number of exceptions. And I've chosen 3 exceptions to go over. Exception 1 being molecules and polyatomic ions containing an odd number of electrons. So for this one, for this example, we are going to use superoxide O2-. So again, we're going to sum up what we have. So in this case, we just have 2 oxygens. We know that each individual one has 6 electrons. And we know that we have a negative charge for this atom, so we're going to add 1 more, which gives us the uneven, unlucky number 13 electrons. So, to get started, we know we have 2 oxygens, and we know that those have to connect at least via a single bond. And then we start filling in our Lewis structure. And we see that we're not going to have enough to fill up each octet completely. So we have 2, 4, 6, 2 from the single bond, gives us 8, 10, 12, and 13. So that's the first exception to the rule. Alright, the second exception that we're going to go over states that molecules and polyatomic ions in which an atom has fewer than an octet of valence electrons. So for this, we've chosen the example beryllium chloride, which is BeCl2. So if we go ahead and sum those up, which I have, we get that beryllium 1 times 2 gives us 2, and for chlorine 2 times 7 gives us 14, for a sum total of 16. So the key note for this one is that when you're filling the octet of a central atom, or if filling the octet of a central atom results in a negative charge on the central atom and a positive charge on the more electronegative outer atom, then you do not fill the octet of the central atom. So you'll see what I mean here in just a second. So we're going to have beryllium in the center because it's the least electronegative. And then that's going to be surrounded by, we have 2 chlorines. So chlorine, and I'm going to draw it off center, but this would be, it would be 180, but just because of space. Actually, you know what? Disregard. So we'll go ahead and connect these, because we know that we have to connect them via at least one single bond, otherwise they're just floating out there in space, lonely. And then we're going to go ahead and start filling in the rest. So we had 4 here, so that leaves us with 12. So 2, 10, gives us 10. 4 gives us 8. 6 gives us 6. And then we have 6 left, so we're going to start by filling in the octet for the outer atoms. So that gives us 2, 4, 6, 8, 10, 12, 14, 16. So this is the exception, being that we see beryllium only has a total of 4 electrons versus 8. And in order to calculate this, we look at formal charge, which the equation is valence electrons minus non-bonding valence electrons minus bonding electrons. So since we know that beryllium chloride has a, this ion has a balanced charge, there's no net charge on it, then these should both equal out to 0, which I've gone ahead and calculated, and they do check out. So we have 7 valence electrons for chlorine because it has a -1 charge, minus the non-bonding valence, so only 1 is bonding, which gives us 6, and then minus the bonding electrons, which gives us 2 that are bonded, but we divide that by 2, which gives us 1, so 7 minus 6 minus 1 equals 0. It checks out. Same thing goes for beryllium. We know that has 2 valence electrons. Non-bonding, well, all of these electrons for beryllium are bonding, so that's 0. And then minus the bonding electrons, which is 4. Okay, and all said and done, that checks out, and it is an equal compound, and that is the exception number 2. So moving on to our last exception, number 3, to the octet rule. It states that this is for molecules and polyatomic ions in which an atom has more than an octet of valence electrons. And the keynote for this one is that when the central atom is on the 3rd row, or 3rd period rather, and below of the periodic table, and expanding its octet eliminates the sum of its formal charges, or the charge in the center, then we should do so. So this is perhaps one of the more complex of the exceptions to the rule. So if we get started, we're going to write our sulfur in the center, and we're doing the sulfate SO4 2- as a -2 charge on it, or 2- charge. We've summed it up. We know that we now have 32 electrons we have to account for. So we're going to draw and connect our 4 oxygens. Okay, so that accounts for 8 of them. And then next thing we're going to do is we're going to start filling these in. So we've got 8 that completes it here. 8 that completes the octet there. But then we have an interesting case where if you after we've done the formal charges, we know that this is what the structure comes out to, and I'll explain why in just a moment. So we're going to end up with 2 double bonds, still completing the octet, so 2, 4, 6, 8. Same thing over here. Because from the formal charges, and we've run it for sulfur, oxygen, and oxygen because they have different individual Lewis diagrams. So that's why we had to do the calculate formal charge twice, to make sure that we end up with a 2- charge, which we know that sulfate has. And anytime you have a net charge on there, you're going to box it in or put the brackets around it and write the charge on the outside. So when you calculate formal charge, you know that this comes out to 0 here, 0 here, and a -1 here, and a -1 here. And that's because from our rule we state that, and from the keynote I mentioned, you want to try and balance the formal charge whenever you can. So that's how we know that even though sulfur ends up with 2, 4, 6, 8, 10, 12, 12 electrons, it can support more than that because it's on that third period or down. So I hope that you guys understand that and learn something. This has been Lewis Structures with Brian Foster, signing off.